Hello and welcome for yet another episode of Profiles in American Funded Research. My guest today is Adriane Lam. I'm excited to have her on to discuss. She got a BS from James Madison University, an MS, a master's degree from Ohio University, a PhD from the University of Massachusetts Amherst, did a postdoc at Binghamton University. I believe that's where you are as an assistant professor now.
Correct. I'm
Is that
still here at
correct?
Binghamton. Yep.
Perfect. Um, so normally what I've been doing is we've been discussing a single grant, but it seems like in this particular episode that it will be useful to discuss a group of grants related to the International Ocean Discovery Program, right? Is that
Mhm.
Yeah,
Exactly.
so I'm excited to discuss this, and maybe I'll let you start by just giving a brief overview of your research and stuff, but I do want to talk about the Joids resolution because that part fascinated me. So I'll let you jump in.
Sure. Happy to. So, what I do, I specialize as a paleontologist using marine plankton, which we call planktic foraminifera. And my lab group and I really specialize in using the times in which they go extinct, certain species go extinct or evolve. And we use those evolution and extinction dates to date the marine sedimentary record. And you can do this with land based rock record too. So that's called biostratigraphy. Bio is life, stratigraphy is putting time into the rock and sediment record. So, what I do and what I've traditionally done is that has allowed me to sail with the International Ocean Discovery Program as someone who tells all the other scientists where we are in time as we drill down through the sediments using these evolution and extinction events of the marine plankton. So that's one aspect of my research. The other aspect is that I'm really interested in what factors in the environment through time influence the extinction of these marine plankton or evolution. And what I'm particularly interested in is the mid latitude regions. So these are areas in the world's ocean, and we usually quantify the mid latitudes as between like 30 degrees to 60 degrees north and south. They're areas that are really characterized by strong temperature and salinity gradients. They're areas where we have a lot of these subtropical water masses meeting more subpolar water masses. And in turn, they create these areas which are called ecotones. So, an ecotone is an overlap of biological communities, two or more biological communities. So, for example, in these mid latitude regions, we have subpolar and subtropical western boundary currents. I work a lot with the Kuroshio Current extension in the Northwest Pacific Ocean, and that's analogous to the Gulf Stream that flows off the east coast of North America. That's our other western boundary current that we're probably all most familiar with. So, what I'm really interested in is do these ecotones, places where we have really cold water populations of marine plankton mixing with warm water populations of plankton, do those mixing of those communities lead to speciation or evolutionary dynamics on longer timescales? Um, so that's kind of the paleontology I'm interested in. And then secondarily, I'm also a paleoceanographer. So my lab group and I also go to places in the last, well, geologic time intervals over the last about 23 million years. And there's warm periods that can behave or be targeted as analogs for warming of today or warming that's projected to come in like the next few decades or so. So, what I also do is reconstruct those western boundary currents that I mentioned and other types of warm water surface currents to see how those warm currents behaved in the geologic past across these geologic warm periods to predict and say something about how they may behave in the coming years and the coming decades. So, we're really looking at the biology through the marine plankton that live in these areas and inferring speciation and extinction, but then also scaling that up to a more broad scale and looking at a whole current system itself and trying to reconstruct that current system. So those are the two main areas of my research program. So with the International Ocean Discovery Program, this is a program that's been around for since the 1960s. So what we do on that, we'll go out on this big drill ship. The last one we had was called the Joides Resolution, and all the scientists, and it's about a party of 25 to 30 scientists that go out, and we're joined by engineers, drillers, people that can operate the drilling system. and also staff that will cook for us. They do our laundry. Like, we're treated incredibly well. So basically, our job out there for 2 months at sea is to simply do science. So we drill sediment and rock cores from the seafloor in different areas of the world ocean, take those sediments back to our labs, and then we can, like, look at evolutionary processes in plankton by extracting them out of the sediments or reconstructing these western boundary currents using various methods and things like that. So your podcast is awesome because it highlights the research we do using federal funds, and the entire International Ocean Discovery Program, since its inception in the 60s, has been funded by taxpayer dollars. So we've been able to do all kinds of earth science research and things over this time span that have really changed the way that we think about our Earth system, and have allowed insight into these long-term processes like the carbon cycle and Earth's temperature changes through time.
So I guess I pronounced it wrong to start. It's Joides or
Joides.
Joides?
Yeah.
Joides. Okay.
Okay.
The Joides resolution.
Hmm.
This now my understanding is that this is a ship that you were able that was it's meant for science. It was meant for science, and it was like rented or something for that purpose. Is that correct?
Correct. There's a company called C1, and C1 are the owners of the Joides Resolution. So the ship was actually built in Canada. I think in like the 60s. No, that's too long ago. Oh shoot. Maybe it was the 70s or 80s. Regardless, it was built for oil and gas industry. But that was a time when the oil and gas industry was kind of going a downturn. So it was retrofitted to drill sediment cores instead. So C1's the owner of the ship. They upkeep the maintenance and everything of it. And NSF had a cooperative agreement with Texas A&M University, and they held a contract with C1 to use the Joides resolution to do about 4 to 6 expeditions per year. And so C1 employed all the drillers, um, all the engineers and stuff that ran the drilling system. And then it was folks from around the world that would come on as a science party and partake in the science and drilling of this, well, analyzing the sediment cores that we recovered.
And I have to ask this question. What is it like spending a couple of months on a ship like that? Actually, it kind of sounds ideal to me that I would have no distractions with my science. Just two months of of straight of working on things. But
Exactly. It is, it's incredible because there's no other distractions around. Like, I love my career, I love my job, but there's always emails are coming up and people need things and students and stuff like that. And I love all of that. But it is so amazing just to go out to sea and just focus for 2 months straight working on science. And the coolest thing to me is there is like you are one of the first people, you are the first person to see these sediments that come up from the seafloor. Um, there was this really exciting moment when I was sailing in the Tasman Sea in 2017. This was IODP Expedition 371. So they all have numbers, sequentially numbered. And the objective of that expedition was actually to drill around the Tasman Sea. And we wanted to reconstruct the timing or figure out the timing of when that big subduction zone. So that's where, like, you have part of the continental crust and the oceanic crust, and the oceanic crust is subducting or being sucked into the earth under that continental crust. Um, how that subduction zone around and on New Zealand, when did it form and why did it form? So we were drilling different areas in the ocean, um, to figure that out. And then our secondary objective was to use those sediments to reconstruct ancient climate in that region back to about 40 or so, maybe going back 60 million years. There was this one site we were drilling. It was the first site on the expedition, and I was sailing as a second year PhD student, so I didn't know what the heck I was doing, and I was really nervous. But there's no better way to learn than to be thrust into these situations. And there's always like really phenomenal scientists who are sailing that you can lean on as like mentors, and like people are just so great. But there was this one site we were drilling, and we weren't sure what we were gonna hit into. So before you do an expedition, we generally have to do geophysical surveys. So these are when you basically take like a CAT scan of the Earth's most uppermost crust, and there's different techniques you use to do this, mostly equipment attached to a boat. Um, so you can kind of see the structures of the sediments and any rocks that are like sub seafloor. So there were some really weird structures that were showing up on these survey lines. they looked like, oh, I don't even know, like really high tip mountains, like you were looking at the Rockies or something. So a lot of people thought, well, maybe it was an ancient coral reef that we were drilling into. We just weren't sure. But we drilled into it and we hit basalt, which is a volcanic rock. And these basalts had all these little air bubbles that were in them. And on top of that, they were reddish in color. When basalt is first erupted, it's really dark gray to black in color because of the dark minerals that is contained within that rock. Basalt only gets these really like big bubbles in them and turns this more reddish color when it's exposed to the atmosphere, so wind and rain and all that. So that told us that this basalt was erupted at or above sea level. So we used the fossils, this biostratigraphy technique I talked about earlier, to date the age of the basalts because it just so happened that some seawater got trapped within one of these cracks in the basalts. Um, and we could extract fossils from that. And then we also looked at the fossils right above the basalts in the sediments that overlie them. And they were kind of nearly the same age. So what we had hit into, what we had drilled, was a basalt flow that we think erupted on Zealandia, which in 2017 was named the newest continent to be defined on Earth. And it's pretty much, it contains New Zealand and some other islands around the area, but the majority of New Zealand sank below the waves when that big subduction zone near there started. So we actually drilled into part of Zealandia and brought it up. Um, so the listeners won't be able to see this, but I'll show you. I keep these pieces of basalt on my desk. So that's like a piece of the basalt that's reddish in color. It's got these big bubbles in it. And then we have the fresher surfaces that were not exposed to the atmosphere that are more like dark gray or black in color. So just really phenomenal findings. And it was such a moment of discovery. Just really an amazing experience.
That actually really is amazing. Effectively, it seems like it was this part was above water, and then maybe because of the subduction was drawn underwater. Is that the yeah?
Exactly. Yeah, and it has to do with like these a little more complex dynamics with like the Earth's crust and how it was kind of like squished together. And then when the subduction zone started, that surface crust of the ocean of the Earth was able to kind of relax back down. And that relaxation back down was the part of Zealandia that then was sank below the waves and has been there at about 1,500 meters water depth ever since.
And so I have a question uh about the using the plankton. So I know, like, as somebody who's is not familiar with dating things other than I have heard of course of carbon dating. What's the advantage of using plankton versus, say, like a carbon dating technique?
Yeah, thanks for asking that. So carbon-14 dating, it can only really be used for the last like 5,000 years or so. So anthropologists, archaeologists, they would use that dating technique if they were looking at like human civilizations or looking at like more recent populations of animals and using their bones. And the reason why it can only go back that amount of time is because carbon-14 pretty much disappears very quickly.
It's the
It's
half has a small half-life in effect. Yeah.
Exactly, exactly. So we can't use it on geologic materials going back, well, pretty much anything like of tens of thousands or millions of years dating. Like that's just not possible because there's no carbon-14 left in any of that material that we study. There's a lot of ways to date things from the rock and sediment record. Um, there are like absolute dating techniques. So this would be like radiometric age dating, where we take a mineral and using that mineral's half life or the half life of the elements contained within it, we can then say, like, we can actually put an absolute date on something. We can say that rock is 3.5 billion years. And there's age error on either side of that, of course. But then there's relative age dating. And relative age dating is just saying something like, this rock is older than another, or it's analogous to me saying I'm older than my brother and sister. That doesn't tell you the ages that we are, but it gives you a sense of sequence of events, right? I was born first, then my brother, then my sister. So biostratigraphy is kind of a relative age dating technique, but it can be combined with other dating techniques like absolute dating techniques. So for example, during Earth's history, there have been flips in the North and South Pole. And those flips in the North and South Pole are recorded in the magnetic minerals in rocks and sediments. So as the sediments are getting deposited, those little magnetic minerals that are mostly contain iron are kind of locked in place and aligned to the Earth's magnetic north or south pole at the time. And as more sediment accumulates on top of them, they get locked in so the minerals don't change direction. So we can go through with these machines, magnetometers. So when we drill a sediment core, we'll place the sediment core through the magnetometer and measure like the orientation of these grains, and we can pick out times of when Earth's north and south pole were reversed. So this is really well constrained now. It's called the geomagnetic polarity timescale. And by combining that with absolute age dating techniques, we know precisely when these flips in Earth's magnetic pole took place. So we've, through time, through the decades, at this point, centuries maybe, have used fossils like marine plankton to also tell us where we are in geologic time. We have to, when we're doing biostratigraphy, what we have to do before we can use those fossils in to infer the ages of deep sea sediments, and scientists have been doing this for a long time, they've been calibrating the evolution and extinction events of these certain species to the geomagnetic polarity timescale. And this is just one way in which they calibrate these events. So if we say, like, okay, the top of this, we call them crons, these areas of reversals. If the top of this cron is at 0 million years and the bottom is at 10 million years, and I'm seeing an evolution of a species right in the middle, well, we can just use linear interpolation and say, okay, that evolved at 5 million years. So we kind of play that game. So we have this information about when these species evolve and they go extinct. So when we're on the ship and we're drilling these sediment cores, they're about 10 meters in length. And at the end of every 10 meters, 10 centimeters, that's called the core catcher. So that's the bit that they take out, not a drill bit, it's the part of the core that they take out, the technicians, when we get a core on the ship, and they'll give that sediment to the paleontologists. So as a paleontologist on the ship, we are the first people to handle that rock or sediment that we drill into. We take that into our paleontology lab. We'll process that sediment. So pull out the microfossils. And there's a team of paleontologists that will sail generally. So I work with plankton foraminifera. Other people may work with radiolarians or diatoms or calcareous nanoplankton or even pollen grains. Um, and I will look for certain species that will tell us where we are in time. So I'm always looking for these first and last occurrence events or these evolution and extinction events. And when I find one, I know where we are in time. So this also feeds back into identifying your reversals through time. So it takes a much longer time to do the magnetic interpretations. You've got to run the core through the machine on the ship. You've then got to interpret these reversals that are occurring in the data. And sometimes that data is very noisy and hard to interpret. But the fossils will tell you approximately where you are in time because the sediment record isn't perfect. You can have gaps in time. So what you think may be a continuous record, it preserves the last 5, 10, 20 million years. You may have 2 to 3 or 4 million years missing at some point in time, which is absolutely normal to encounter in deep sea sediments. So you've got to use your fossils to also help interpret where you are in the geomagnetic polarity timescale. So again, going to that example I used, we use linear interpretation to say, well, this species evolved at 5 million years. If I see this big magnetic reversal and I'm like, what is this? But I see that same species occurring there, I can go, okay, where it's been calibrated in other places to the geomagnetic polarity timescale in other places, I know that this evolution event is happening within this cron, this reversal, and then we know where we are in the geomagnetic polarity timescale, and then we can get a really more robust or bigger confidence interval of where we are in time, in geologic time. So it's an art form. It also involves being able to really tell, one species from another. That's called taxonomy. So we do a lot of that too, because a lot of these things look the same when you look at them, especially for the first time.
So the another question that I had is why plankton? And I'm assuming maybe it has to do with abundance or something like that, but I'll let you take that.
No, you're right on. It's because they're so abundant in seafloor sediments. In fact, some of the sediments that we have at the seafloor, we call them carbonate ooze, um, which sounds kind of gross, but these plankton that I work with secrete their shells or test out of calcium carbonate. So the chemical formula is Ca, so that's a calcium, C, carbon, O, oxygen. So CaCO3, there's 3 oxygens in there. So basically, that's the same mineral, or I'm sorry, that's the same chemical makeup as limestone. It's a rock that's really common that forms on like tropical beaches today. Our reefs and corals are made out of the same thing. So they preserve, calcium carbonate preserves extremely well because it's a hardened mineral. So our seafloor, when these tests of the marine plankton, which live in the surface ocean, so in the very thin layer, warm layer of the ocean called the mixed layer, and down through the thermocline. So the thermocline is that transition zone between the warm surface mixed layer into the deep ocean. So they live across along that gradient. So when they die, these things only have a lifespan of a couple weeks to maybe a month, their shells float to the bottom of the seafloor and collect there over millions and millions of years. So they're incredibly abundant. Like can take a little scoop of a sample in some of these calcium carbonate oozes, and it's almost 100% planktic foraminiferous shells and tests, and then also nanoplankton, these really, really tiny plankton that you need an even higher powered microscope to look at. Um, so you can find these carbonate oozes everywhere in the world ocean. But where you can use them, where they do collect, you're right, they're extremely, extremely abundant. And so there's just plenty of them literally for the picking because we pick them out of the sediments.
And I noticed that the that it sounded, or from some of the stuff that I read, you can correct me if I'm wrong, but it seems like there's an X-ray machine on board the ship. Is that true?
There is, yep. There's the X scanner. And that's something that was only on the ship for not a very long period of time, just for like the last couple years. So we can actually put sediment. So, okay, when we get a core, it's brought onto the ship. It's brought onto a place called the catwalk. And so the technicians bring up the core, they lay it on these arms on the catwalk, and they cut it into 1.5 meter segments. And that's because 1.5 meters is just way easier to handle than like a 10-meter core. So we will let those sit in racks for about, well, a couple hours until they kind of equivalate and come to room temperature. Once they do, we cut them in half. And they're laid then on the table in the sedimentology lab. So the sedimentologists, as appropriately they are named, they look at the sediments and quantify its color, composition, what minerals are there, are there any large fossils they can see, things like that. So one of those halves of the core will then be put into the X scanner, and the X scanner kind of uses X-rays and goes around to give you you basically can see inside of the core. So for example, last summer I was on IODP Expedition 403, and that was to the Fram Strait. So we were drilling off the coast, the west coast of Svalbard, really high latitudes, and there are so many rocks in the sediments, and they were all dumped there by glaciers that moved across the ocean off of Svalbard and dumped all these rocks there. So it was really kind of cool. So you could look at the surface of the split core and not see a whole lot. But then when you put that core half into the X-ray scanner, the X scan, you can see all of the rocks that are there below the surface that you couldn't normally see. So it's really given us like a literal, more inside view, an in-depth view of the sediment cores and the structure of the sediment itself and what rocks and fossils could be contained within them. So it was pretty revolutionary. We had a lot of fun with that.
Yeah, it's amazing that that you can, get an X-ray machine working on a ship. That's impressive.
Yeah, it was really cool. And I have this funny story. I probably shouldn't share here, but like whatever. It's funny and in the spirit of scientists laughing at themselves. So I was on this, handling the X scanner and putting sediment cores in and out, and it's kind of tricky to take them out. So we have this like homemade 3D printed method. It kind of looks like a pitchfork device. So you kind of push it against the end of the core, and there's a cap on the end of the core section, and it's supposed to grab onto it and pull it out. Sometimes it doesn't work so great, and I was trying to get this pitchfork like thing around the core to pull it out and kind of twisted it. Well, I dumped almost the entire sediment section into the X scanning machine, and I was like, oh my gosh. And so one of our co-chief scientists, who's also my friend and colleague, Kristen, came by. She's like, "Are you okay?" And I was like, "No, I just dumped the sediment into the X-ray machine." And she goes, "Oh no." She's like, "I'm sure this has happened before and they can get it out." And I'm like, "Okay." So when the technicians came inside, one of the lead technicians, I was like, "Beth, I'm so sorry. I have dumped out the sediment into the X scanner." And she goes, "Well, that's never happened before." And I was like, "Oh no." Like Here, I was really hoping this had happened before and there was some sort of precedent set, but nope, it was the first time it happened. So, anyway, the techs are amazing. They were actually able to get out the sediment, keep it kind of in order and cohesive, and put it back into the core. And it really looked like nothing had happened at all. So, yeah, it's an amazing machine, but I got pretty sick of it early on because I became fearful of this thing.
That's fair. So before this was on the ship, did you have to take the wait until you got back to shore and take the course to do X-ray scans that way, or did you just not bother with the X-ray part, or
Yeah, I think so they, and when I say they, this is at the Texas A&M Core Repository. So the Gulf Coast Repository is one of three repositories around the world where we keep our IODP cores. So the one down at the Gulf Coast Repository on the campus of Texas A&M, they built that X scanner there at the core repository specifically to be put on the ship. So if you wanted to do any X-ray scanning, you had to take it to like maybe another lab that had these scanning capabilities. I know some other researchers and colleagues of mine were using like medical facilities to use their like X-ray machines. But when we got that on the ship, it was really incredible. So now that the ship's been decommissioned, so Expedition 403 was the last expedition of IODP to run on the JOIDES resolution. All of the equipment on the ship that belongs to Texas A&M went back to that core repository in College Station. So we'll still have the ability to scan and x-ray these cores. And the cool thing is, now that it's back at the core repository on land, and it's in this facility where it's literally right beside all these big refrigerated rooms where we keep the cores, we can go back to older cores now that we drilled when we did not have this x-ray technology and rescan them to look at like what's inside of them and kind of take a deeper dive into them. So that's really kind of cool.
that's nice. So are there plans to um, commission another ship in lieu of the JOIDES resolution, or has that
Yeah.
just been stopped?
It hasn't been stopped. There's a lot of challenges to face. So the program itself, IODP, takes about 72 or so million dollars to run every year. NSF, through its Ocean Sciences program, has about 48 million that they allocate towards the program. So the rest of that money to get to 72 million was sought from our international partners. So that included the UK, Australia, New Zealand, and Japan. All in all, we had 23 partnering countries within IODP. But our partnering countries, a lot of them didn't re sign a new agreement to continue putting money into the program for various reasons that I'm kind of unclear on. Um, so basically, NSF was in the US was left funding these expeditions by itself. But you can't run a program of that scale on only $48 million when it takes about 70 some million to do it. So right now, what we've done, NSF has set up this kind of task force of scientists, geoscientists, to envision and survey the community and see like if we get another ship that has the technology to drill deep through the water column and then further deep into the sediments. It's called riserless drilling. If we get another riserless drilling vessel, what do we need that vessel to have? What are the labs that we want to have? What equipment, drilling technologies, and things like that. So they're working on it. Um, it is going to take a lot of money and funds. So the JOIDES resolution was not built by the US, but they are aiming to have a ship that's built in the US by the US. So it'll take a little bit of time because, these things take a lot of time, but they are thinking about it and planning for it for the future. In the meantime, we're running in what we call mission specific platform mode. So, a mission specific platform is any type of vessel or any type of drilling platform that we can use for scientific ocean drilling. So, for example, there's these smaller ships that do a different type of coring technique called piston coring, and they don't go as deep into the sediments, and you can't use them in like really, really deep water systems, and they for certain can't drill into rocks. But that is something we could use to collect sediment records that would cover like the last maybe couple of million years, the last couple of tens of thousand years, depending on how fast the sediments have accumulated through time, how fast that sediment or how thick that sediment package is. So that could be used to hold us over. We also have these platforms that you can deploy out into the ocean that just kind of sit there. And they can drill about one or two cores really in a close area. Um, so we are using that kind of method there's an expedition going this summer. It's under a new IODP program called IODP Cubed. It's between Japan and ECORD, the European countries, and they are going to drill off the New England coast. And what they want to do is look at groundwater flow that's coming from the continent in through the sediments offshore and how groundwater is kind of moving through those systems and going out into the ocean. So my PhD student is actually a part of that expedition. So they're using one of these mission specific platforms, so which is literally a platform you sit out there and it'll get moved by a boat, but they are good for drilling in shallower waters. So this is actually pretty ideal for them. So we're kind of getting creative in the meantime to hold us over. And there's also being a lot of money allocated and resource allocated to go back into the core repositories, collect more data and more samples from cores that were drilled by the first scientific ocean drilling program, the deep sea drilling program, which dates all the way back to the 60s. So we're going back into the core repositories and using what we call this legacy material, so material that we have laying around, to apply these newer methods to the sediments and to the fossils that were not around when these sediments were drilled. And I think that's a really phenomenal opportunity too, to use the sediments that we have. I mean, every expedition that we run, and this is a little outdated numbers, it's pre-pandemic, these expeditions are about 12 to $15 million each. So we invest a ton of money, taxpayer dollars, into running these expeditions. So we definitely want to get the bang for the buck out of them. So it's very cool that we can go back to older cores and still use them.
Now, how are you able to now, because you discussed the ocean currents, how are you able to kind of reconstruct those currents? Is it related to like this type of fossil was if it was a certain temperature, like so this whatever like plankton or whatever only grew at a certain temperature or something like that? Is that sort of the idea of how you can kind of reconstruct those ancient currents?
Kinda. So when we go to reconstruct these currents, I use a different technique called geochemistry. And this is a big field of geoscience research where you're using like the chemical signatures from fossils and rocks to make inferences about, for example, temperature, atmospheric CO2, salinity, things like that. So you use the chemistry of these rocks and fossils and sediments to reconstruct the environmental variables. So I'll talk a little bit about my accrotio current research. So this is in the Northwest Pacific Ocean. So in 2001, my PhD advisor was on an expedition on the JOIDES Resolution, and they drilled a series of sediment cores that transected the modern day position of the accrotio current extension. One of those sites was on the southern end of the current, so in warmer water masses. One of those sites was directly underneath the modern day position of the accrotio in kind of this mixed kind of temperate water mass from the meeting of the cold waters and warm waters. And then the third site was on the northern edge of the Kuroshio Current in more of like subpolar water masses that were being brought down from the Arctic. So what I did for my dissertation research is I picked fossil plankton from those three sites from 5 to 2.5 million years ago. And we did this, we took one sample about every 15,000 years. Then we consider that a little lower resolution, but it was a 2.5 million year long interval. So it was a pretty long interval to investigate. So what I did with this was use stable isotopes from the planktic foraminifera. So the species of plankton that I used are those that live in the very warm mixed layer, the little skin of the ocean that's the warmest. And they pretty much monitor the environmental conditions by incorporating the chemistry of the water into their shells when they secrete their shells. So when we go back and pick the plankton from these sediments of the time we're interested in, we use stable isotopic analysis. So that's oxygen and carbon. And for oxygen, we're looking at the ratio between oxygen 18 and oxygen 16. For carbon, we're looking at the ratio between carbon 12 and carbon 13.
And when you
So
say stable, does that mean is that because the it has a very long half-life? Is that what the idea is there?
good question. These mean that they are not giving off radioactive energy at all. So stable means that they're not changing. They're not losing any energy over time. And there is a set amount of carbon 13, carbon 12, oxygen 18, oxygen 16 in the environment. So that makes it so that we can measure the exchange of oxygen 16, oxygen 18, and we call the fractionation of those isotopes, one from the other, in the environment and the processes that do that. So one of the ways, for example, you can fractionate oxygen 18 from 16 is by cooling down the earth and growing ice. Oxygen 16, it has less protons in the nucleus, so it weighs less than oxygen 18. So it's a mass kind of difference that will separate these two. So oxygen 16, because it's lighter, when water evaporates from the surface of the earth, preferentially oxygen 16 evaporates. As that water is then carried over the continents or to different areas and rained out, oxygen 18 will be rained out first because it's heavier. So that means that when you form snow in the high latitudes or high altitudes, it's enriched in oxygen 16 because it's that lighter isotope that made it that far. So during cold periods in Earth's history, you take more oxygen 16 out of the oceans and store it on land in the form of ice and snow. So that means that your oceans are more enriched in oxygen 18. So by using the ratio, measuring the ratios of oxygen 16 to 18 through time, we can infer times of when that spot in the ocean was cooler or warmer. And that's exactly what we did to reconstruct the Kuroshio current, because we were going to look at changes in the latitudinal shift of this current to the north or to the south in response to warming and cooling through our study interval. And we found that, yeah, during warm events, it does warm and the current might shift northward. And then as the Earth cooled back down, the sites did cool, and we think that that entire gyre system that the Kuroshio current is part of also kind of shifted towards the equator and kind of became more depressed. So the other cool thing that we've been doing with the Kuroshio current in these sediments, actually my first master student, Charlotte, she did stable isotopes at one of these sites, the northernmost site on the Kuroshio current that was drilled, and we did stable isotopic analyses of the marine plankton. We did one sample every 3,000 years. So my previous study was one sample every 15,000 years or so. And we took that stable isotopic signature, and there's a certain like different equations and tools online where you can convert that into temperature. And that's exactly what I did with her data. And we found that the Kuroshio current across this analog warm period with atmospheric CO2 values similar to today, that current warmed by about 1.3 to 1.9 degrees Celsius across this warm event. Today, from the instrumental record, so satellite measurements of sea surface height and sea surface temperature measurements that go back about a decade, we know that the Kuroshio region has warmed and the current has warmed by about 1 to 2 degrees Celsius. So that tells us that in the Middle Pliocene, this interval that we were looking at from 3 to 3.3 million years ago, the current today has already reached the degree of warming that it did during this analog warm period of the past. So that means if we continue warming, which we're projected to do because we're still emitting CO2, right? That current's going to warm even more, but I don't know the degree to which it's going to warm because now we're past warming of levels that we measured during the mid Pliocene, 3.3 million years ago. So now we're kind of like, okay, I guess we have to go back even further in geologic time to even older sediments when Earth was much warmer, with atmospheric CO2 levels around maybe 500 to 600 parts per million, to really begin to further understand how this current will continue to warm and change under even more elevated atmospheric CO2 conditions. And so, again, just tying it back to your podcast, like that was all we were able to infer that all because taxpayer dollars were put into science, into NSF, and used to fund these big expeditions that we can drill these sediments with. Um, and I'll also add, like, riserless drilling, like we did on the Joyce's resolution, is the only way in which we can get these deeper time sediment records because they're way deeper down in the sediment column. And it's those deeper records where the Earth reached really high levels of atmospheric CO2 that we need to get and continue recovering so that we can continue to infer, how these ocean currents are going to behave, how marine ecosystems are going to change under increased warming.
Now, can you give a kind of, do you have a enough of uh of a um resolution, I guess is the word I was looking for, enough resolution to tell uh if you were to compare the time period of the current time period that we're in to that period of like 2 3 million years ago, how fast is the warming happening? Is it much faster now than it was then?
Oh yeah, yep. So I also work around deeper time mass extinction events, and I teach a mass extinctions course. And I hook students with like, oh, dinosaurs, fossils, And then once they're in the class, I'm like, I got you. Now we're going to talk about climate change. So, but I teach them, what happens when you release a lot of atmospheric CO, release a lot of CO2 and other greenhouse gases into the atmosphere, because that's pretty much what's happened during every mass extinction, the big five mass extinctions throughout Earth's history. Um, they've all been caused, except for one, by massive releases of greenhouse gases through volcanism. Um, so the rate of warming today is unlike anything that we've measured in the geologic past. So there are very few events, if any, um, over the history of Earth in which we see the rate of warming that we're seeing today. Um, it's pretty unprecedented what we're doing today to the atmosphere and to our Earth. There's really no true analog for that in the geologic record. There are, like I said, we work across analog warm periods during times in which Earth's atmospheric CO2 reaches levels of today or in the near future. But when we think about the rate at which that warming has occurred in the past, it was much slower. Have been times like the end Permian mass extinction. We had a huge amount of greenhouse gases released into the atmosphere, and it did happen pretty quickly, and it led to ocean acidification, deoxygenation of the oceans. We had a lot of we find mummification of animals that try to escape the heat in the terrestrial realm. There's just no food resources. These gases also eroded the ozone layer, so there was UVB radiation that we think led to the mass extinction event. I mean, the Permian mass extinction is the biggest mass extinction. 98, 97, 98% of life went extinct. So that's like 9 out of 10 species went extinct during that time. So it's crazy, wild extinction. But the rate of warming during that extinction event still does not match the rate of warming that we're seeing today. So it's dire. Yeah.
So now, of course, and you've kind of already hinted towards this because the podcast, of course, is related to funds. So, but could you explain to us what specifically? And I know that the grants that you got were relatively small grants, but what specifically those funds were being spent on?
Sure.
Labor, travel, these kinds of things.
Mm-hmm. All of the above, really. So we use part of those funds. Well, let me back up and explain to listeners what they are. So the funds that we get after sailing are called Post-Expedition Activity Awards, or P awards, and they're up to $20,000, and they can fund. Basically, they're for pilot projects, and the hope is that you use the data that you get from these P grants to put into a larger NSF grant to continue doing the science on a bigger scale. So we use a lot of that money for supplies in the lab. So we use, chemicals, a lot of consumables. We have to use vials to store our samples long term, archival ink pens. None of it's particularly expensive, but it does add up. I've also used those funds to pay undergraduate students. So when we come back from an expedition, we will sample the cores that we drill a few months after the expedition, and those will be mailed to us. So I actually have 4 boxes of sediments, sampled sediments in my lab right now that need to be processed over the summer so we can extract the fossils. Um, and that's a lot of work. So I've paid undergraduate students to come into the lab and just wash our sediment samples for us to help us get the science going, which is wonderful because it's not only paying them some funds, but they're getting experience in a lab setting. And it's kind of helping capture and train the next generation of scientific ocean drilling scientists, because my hope is always they'll get really invested in the research and want to continue doing a research project with me. And a lot of times they do. Um, a lot of the analysis or a lot of the money also go towards analyses itself. So the stable isotopic analyses I was talking about earlier, a lot of funds go towards that. Um, and a lot of our funds will go towards measuring the sizes of the grains themselves in the sediment, so grain size analyses. So that's where a lot of the money goes. And that once we have that data, I've got 3 NSF grants pending right now, so under review. All of my PhD students, I've got 4 right now, they are going to write their dissertation prospectuses. So it's a document that outlines what they're going to do for their dissertation research to earn their PhD. So we're going to take those documents and flip them into NSF grants too and try to get them onto some funding and have money for their research. So all the data that we're obtaining from those P grants are feeding into their training as well, and their ability to provide really good preliminary data in their dissertation prospectus and for their future NSF grants. So we've done a lot with the grants. I mean, the entire lab pretty much runs off of federal funded grants. The university doesn't have a lot of internal funds, and that's true for most universities, just of the way we operate. We're encouraged to seek external funding. Um, so we use a lot of that funding, a lot of the NSF grants too that I've got pending will pay graduate students, undergraduate students, and postdoctoral researchers. And there's also a big chunk of that, the NSF grants that we win, also goes towards back into the community. So for some of these pending grants I have, I've proposed to do a temporary museum exhibit at the Museum of the Earth in Ithaca, New York, part of the Paleontological Research Institute. So if I win one of these grants, I'll work with the PRI staff there and artists that they commission to make this temporary display of like mass extinctions. We have another one that's pending where we would do an exhibit on ocean currents and how they change in a warming world. So we'll incorporate our research into that, but we're also like interacting with the public. And we've also proposed to do programs where we work with like K-12 educators in the area. So it's not just the public who goes into museums, but we're going into the classrooms and teaching students about Earth's history, getting their hands on fossils, and just like getting to interact with different scientists, I think is really important. Um, so we give a lot back to our communities too, which is something like my students and I are really happy to do and glad that we have the opportunity to do so.
That's fantastic. I love that. Having kids in school myself. Actually, I've gone and talked to my son's class. They've never asked me to talk to my daughter's class, but I've gone and talked to my son's class, and the kids, especially he's 8 years old. So especially at that age, they're still so full of curiosity, and so always a joy to interact with people who are still curious, I guess.
It is, and they are so funny, and they ask the best questions, and they all want to know about dinosaurs, and I'm like, I'm so sorry to disappoint. I don't work with dinosaurs. I work with marine plankton, which probably to them is not anywhere near as cool as dinosaurs. But yeah, they're wonderful. I love working with the kids. Yeah, it's a breath of fresh air almost to get out of the university, and go work with them. And you're like, oh yeah, they are so curious and they do really love this stuff. So I love the passion that comes through too. It's so much fun.
And last question for you, because I'm quite interested in this topic, is how did you get interested in science? What was your path? Maybe if you could map back to high school or earlier.
That's a good question. So I was always like the weird kid at school, like, while other girls were into like doing their hair and exploring clothing and everything like that. I was like out with my brother in the woods finding dead bugs for his bug collection, and like I would keep some bugs for my bug collection. I remember going over to my grandmother's house. She had 14 acres out in the country, and I would always beg her to please buy me plaster because I wanted to find the deer footprints, the fox footprints, and I would like mold them, make molds of them. And I remember having this drawer or two in my dresser in my room where it was like my little natural history collection. I had all these rocks and stuff that I had collected. So I didn't do great in high school. I actually like really hated high school. I would always skip class and I'd go riding by myself, our horses, because I wasn't into it. But I knew for my career I wanted to do something where I could make an impact on other people. I didn't want to be stuck in an office. I didn't want a 9 to 5 job, and I wanted to travel and meet different people. So I considered going into the medical industry, and then I was like, no. I considered being like a graphic designer. Um, I didn't really know what I wanted to do. And because I had skipped high school so much, my grades weren't great. So I went to community college, which ended up being a phenomenal decision. Some of the best classes of my life, some of my best professors that I've ever met were there in community college. And they whipped me into shape. It was great. It was like the training that I needed before I went to a 4 year university. And it was there that I had to take a science class, and geology was one of the options. So I did. I took this geology course, and I'll never forget the professor, Dave Walls. Just funny. I mean, just had this like sharp wit, really smart, but he, like every class, I was just cracking up. But I really enjoyed him as an educator, and I really enjoyed the subject material. So I kind of thought, maybe I want to be a geologist. And it was during the second class that I took with him. It was like the next step up from intro geology, historical geology. We went out into this nearby land, and this guy was totally fine with us coming onto his land. He had a creek that ran through the property, and that creek cut down into these sediments and rocks that contained fossils from about 15 to 20 million years ago. So we were finding these big shells, these big gastropod shells. He told us we could find shark's teeth. I didn't find one, but I was absolutely hooked. And I was like, okay, I'm becoming a geologist. Um, so Virginia has this great program where if you get like above a 3.5 GPA in community college, you get automatic admission into any of the state schools. So that's when I went to James Madison University. And like you have to understand, I did not research these programs at all. I was just like, I want to go to JMU because it's in the Appalachian Mountains of Virginia and I love that area. Like that was my reasoning. So I ended up going there. I took a paleoclimate course with Kristen St. John. She was a professor that taught the course, and that's the first place where I learned about scientific ocean drilling and the Joides resolution. And I remember sitting in class and going, "Oh my gosh, I want to sail on that ship. I want to do that." And we got to work with real sediment cores drilled from the Gulf of Mexico. I loved doing that. And so I pursued an independent research project with her, conducting a planktic foraminiferal biostratigraphy, looking at the first and last occurrences or evolution and extinction of the plankton in that core through time. And I got absolutely hooked. So I got hooked on marine plankton from a very early part of my career, in my educational path. So I also took a paleontology course and got really hooked on marine invertebrates in deeper time. And I was like, okay, I want to go to grad school, but I'm not sure which path to take. So I ended up doing my master's at Ohio University with Alicia Segal. And that's where I worked with marine invertebrates from about 450 million years ago and using like statistical techniques and modeling methods to infer like their evolution types and how they moved across the global ocean. But I knew I really wanted to still be a paleoceanographer. I really wanted to do biostratigraphy and go back to working with marine plankton. But I also wanted to make money. So I went to this conference in, gosh, it was either 2014, it must have been 2014, and it was this oil conference. And it was in Colorado. So two of my friends and I drove across country. It was a wonderful experience and went to this conference. And it was there that I realized I don't want to work for oil and gas. That's not really my goal. I really want to work to, reconstruct ancient climates and look at evolution and do the research. So I had worked with my PhD advisor as an undergraduate student while at James Madison. I didn't go to him for a master's because he just didn't have funding at the time and he had a full lab. But he told me when I was an undergrad, come email me again when you're ready to do a PhD if you want to do one. So it was at that conference I emailed him and I said, how about doing that PhD? I didn't say it in those terms, but that was basically the gist of the email. And he said, now's the perfect time. I'm having a lot of my students graduate. So UMass Amherst was the only place I applied to for my PhD because I figured if I couldn't be a paleoceanographer and planktic foraminiferal biostratigrapher, I didn't want a PhD. It was a risk and a huge one, and I don't recommend that strategy to anybody. But I got in and I got fully funded to do my PhD, and it all worked out great. So, luck. It was based on a lot of luck how I kind of found my way into this career and kind of stumbled my way through. And I'm just really grateful for the people along the way that were like, helped like inflame my passion and gave me these opportunities to do research, which led to additional opportunities. And eventually me sailing on the Joides twice. So it was great.
Well, thank you very much. I think this was a great episode, so I appreciate you coming on, and I hope to see you again soon.
Thank you, Jeremy. I really appreciate the opportunity.